Modern neural networks are capable of stunning accuracy, but they have a massive flaw. We rarely understand why they make the decisions they do. They operate as impenetrable black boxes, taking in data and spitting out answers, leaving us to guess at the logic hidden inside. To understand why this is a risk, look at an anomaly known as the clever Hans effect. In one notable case, an image classification model successfully identified horses with high accuracy, but researchers found the network wasn't looking at the horses at all. It had learned to look for a specific source tag that happened to be in the corner of 1/5 of the training images. Put that tag on a picture of a car, and the model would call it a horse. We need a way to look inside the model and confirm exactly what it prioritizes. This is where gradient-weighted class activation mapping, or Grad-CAM, comes in. By running an image through the network and tracking the internal math, Grad-CAM produces a visual heat map that highlights the exact pixels driving the model's final decision. By mapping the model's focus, we stop guessing. We generate visual proof showing whether the network learned the actual physical features of a subject, or if it is simply exploiting a misleading correlation hidden in the dataset. This flowchart details the architecture of Grad-CAM. An input image passes forward through a convolutional neural network, generating a series of activation feature maps along the way, ultimately resulting in a final classification score. Unlike older methods that required specific network structures, Grad-CAM works backward from that final score. Because it relies entirely on gradients, the mathematical derivatives that track how much each feature affects the output, it can be applied to virtually any arbitrary CNN architecture without modifying the model itself. Here is the mathematical foundation for that process. To isolate the features that matter most for a specific target class, we compute the gradient of the class score, designated here as y to the power of c, with respect to the two-dimensional feature maps, a to the power of k. These gradients are then pooled. By taking the global average across the width and height of those maps, we generate a specific set of alpha values. You can think of these alpha values as importance weights, dictating exactly how much each feature map contributed to the prediction. Finally, we multiply our activation maps by those importance weights and pass the sum through a ReLU activation function. The ReLU function zeroes out any negative values, ensuring we only keep the positive features that directly support our target class. Through this sequence of operations, we translate the abstract concept of gradient loss into a highly readable two-dimensional spatial map of importance. To execute this in PyTorch, we start by loading a pre-trained ResNet34 model. We then set up a series of pre-processing transforms to resize and normalize our input image, converting it into a tensor ready for inference. Before we run the data through, we have to decide where to intercept our gradients. For a standard Grad-CAM implementation, we target the absolute final convolutional layer, ignoring the intermediate or fully connected layers. In ResNet34, we specify layer 4. This final convolutional layer holds the highest level spatial and contextual features. It represents the model's most complex understanding of the image geometry, right before those spatial dimensions are flattened out. Next, we use a PyTorch utility called register hook. During the backward pass, PyTorch actively calculates gradients. The register hook function acts as a trap, capturing and storing the gradients for our specific layer as they flow past. By placing this hook precisely on layer 4, we isolate the exact mathematical moment where spatial recognition transforms into an abstract classification score. Let's test the pipeline on a complex input. We'll use a single image containing both a dog and a cat, creating a dual-class challenge to see if the model can physically separate its reasoning. This sequence shows the result when we instruct the pipeline to explain its prediction for the bull mastiff class. The raw map isolates the dog's face, completely ignoring the cat lying in the foreground. Because the final feature map is incredibly small, usually just 7 by 7 pixels, we upsample the output to perfectly match the spatial conventions of our high-resolution input image. This second technical sequence shows the exact same pipeline, but instructed to explain the prediction for the tiger cat class instead. The hot zone immediately drops entirely off the dog, moving down to map specifically to the body of the cat. This proves the model possesses distinct, isolated spatial awareness for multiple objects within a single frame. Grad-CAM's utility lies in this exact selectivity, identifying exactly what pixels drive each individual class score. We can also run edge cases to see how the network builds its understanding. Let's see what happens to the heat map if we hook the gradients at an intermediate step, like layer 2, instead of the final layer. This visual output shows that by tapping layer 2, the coherent shape of the target completely breaks down. Instead of a dog, we get a scattered, pixelated field of noise spread across the image. Early layers in a neural network do not understand context. They detect low-level primitives like basic edges, lines, and textures. It takes the deeper layers to assemble those primitives into high-level objects. Returning to the final layer, we can look at this text output and heat map for a highly confident prediction. For an image classified as a tiger with an 88% probability, the hot zone heavily blankets almost the entire body of the animal. Look closely at the model's second highest prediction for the exact same image, tiger cat, at 11%. Depending on the class-specific features the network is searching for, its attention can easily shift or encompass different proportions of the subject. Grad-CAM serves as a comprehensive audit tool. It allows developers to definitively check if their network is focusing on an entire, correctly identified object, or if it is being misled by a fragmented background detail. We no longer have to accept the output of a neural network on blind faith. We've moved from treating models as completely opaque boxes to generating verifiable visual proof of an AI's internal attention mechanism. However, interpretability requires diligence. Always perform sanity checks on your models. Visualization techniques can sometimes produce compelling heat maps, even for networks with completely randomized weights. You have to ensure the maps reflect actual learned parameters. If you encounter artifacts or find regions the model highlights improperly due to gradient averaging, you can explore advanced alternatives like Grad-CAM, which refines the mathematics using element-wise products. Take this PyTorch pipeline and apply it directly to your own custom datasets. Examine the heat maps, check the gradients, and confirm your models aren't learning the wrong correlations. In modern AI development, achieving high accuracy on a testing set is no longer sufficient. To deploy reliable models, you must also mathematically and visually prove that they are right for the right reasons.